All right, here in podcast 10.2, we're going to talk a little bit more about solutions and the process of making solutions and some different types of solutions. And a quick little intro into the solubility graphs that you see there on page 6. We're not going to finish that whole page with all the different types of questions, but I just want to help you kind of relate that information to what we've already learned, because reading these graphs is really going to be pretty easy. We're going to be doing that and one other new thing in class next time, so wanted to get you that little bit of an intro. But to start things off with, we need to understand that there are different types of solutions based on how much stuff is dissolved in them. And all of these words for the different types of solutions are based on this word saturated. So let's go ahead and start with our second definition here. A saturated solution contains the maximum amount of solute. That word saturated for us here just means full. Like if you have a sponge that is saturated with water, it's full of water. You can be saturated with information. You're just so completely full of information. Your brain feels full. That's all that saturated means. So knowing that, when we're talking about unsaturated solutions, those are solutions that are unfull, or the ones that contain less than the maximum amount. They're not full yet. And super saturated solutions are super full solutions. Somehow they contain more than the maximum amount of solute. And it is important to understand that supersaturated solutions don't just happen. You can't just keep pouring salt into water and come up with a supersaturated solution. That salt will dissolve until it's completely full, until that solution is saturated, and then it'll stop dissolving. You'll just be left with salt at the bottom of your cup or at the bottom of your pot of water if you're boiling water or something. So normally, under normal conditions and normal chemistry stuff, we're dealing with unsaturated solutions, and maybe we get to saturated, but we almost never see a supersaturated solution doing normal chemistry stuff because you have to put some effort into making it supersaturated. So that extra special note there, something special has to be done to make a supersaturated solution. It's not just a normal thing that happens if we keep stirring or mixing or adding stuff. So this is the basis for what we're going to be talking about today. And one of the biggest ways to tell these solutions apart is how they act if we add a little bit more solute, just a crystal, a single grain of salt more, to a solution that is saturated, unsaturated, or supersaturated, and deciding what is going to happen. And for these situations, I think it's kind of useful to imagine our solution as a person eating, because it's kind of easy to understand when you're eating, when you're full. Your body tells you when you're full. And if you are full, you are saturated with food, and someone comes and offers you one more hot dog. Let's say we're at a barbecue or something. It's just like adding a crystal to a saturated solution. If you really are full, and I know some teenage boys and just teenagers in general might not have this thing that we call full. You might never reach that point, but that's because you're growing. That's more complicated there. But for a normal person that gets full and is done eating at some point, if you reach that level and someone offers you something else to eat, you'll probably politely decline. No, thank you. I've had plenty of hot dogs. And our saturated solution will do the same to that crystal. No, thank you. I've already dissolved enough here. I don't need to dissolve any more solute now. So if we add a crystal, just a little bit more solute, to a solution that's already saturated, it's just not going to dissolve. And that's what we were talking about earlier. The salt will just sit on the bottom of my beaker and not do anything. If my solution is unsaturated, though, just like if you're at a picnic and you're not full yet, and someone walks around and offers you a hot dog, you're probably going to thank them, saying, yes, I was hungry. I would love to eat that hot dog. And an unsaturated solution will do the same with that crystal. Sure, I've got room. I'm not full yet. I'll dissolve you. No problem. So, crystal dissolves in an unsaturated solution. Now, what if it's supersaturated? Imagine you went to this picnic with your family and friends, everyone, and you managed to get supersaturated. Like, there was a point when you thought, oh, that's the perfect number of hot dogs. I am full. and then someone came around and offered you more, and for whatever reason you managed to force down a couple more, you were helping, and they had some more to eat. But one way or the other, you got super saturated. You're sitting here thinking, oh, why did I eat those 4 more hot dogs? Regretting some of your life choices because you are over what you would normally consider full. And then someone comes around and says, oh, please just eat this 1 more hot dog. If they try and shove that down your mouth after you're already over full, not only are you probably not going to accept it and say, no, I really can't handle that. I don't want to dissolve that anymore. I'm already super full. But there's a good chance that if we really tried, if you even put that in your mouth to try to eat it and dissolve it, that a lot of that extra stuff you'd managed to hold down already might just come right back up. And it's a lot prettier with a solution, but the same thing will happen. All that extra solute, whatever was above what we considered saturated, above full, is going to come out. So it's like the straw that broke the camel's back. We add one more thing, and then suddenly all that extra stuff just comes piling off, falling out of our solution. And it's what we call recrystallizing it, because it was a crystal, then it dissolved and it wasn't a crystal anymore, and now that it's coming back out of solution, it's recrystallizing. So all we've got to do to be able to tell our solutions apart is add just a little bit more solute to it, and how it acts, how it behaves, will tell us how full it was. So a couple other kind of random words here. You've already seen the word dilute earlier in the packet. Just want to make sure we understand what that means, because it's kind of related to these words. Dilute means we only have a small amount of solute in the solution, so way more solvent than solute. And these do tend to be unsaturated if we have a super duper small amount in there. Concentrated is the opposite. This is when we have a large amount of solute in solution. But we can actually have a solution be saturated while it's still dilute. And it's important that we key in on what these words mean. Saturated means full. Dilute means it's small amount. So a solution can be full while still only containing a small amount if that solution kind of has a small appetite. If you can just take 2 bites of food and be completely full, then you can eat a small amount and be full. And the same with our solutions. Our solution can be saturated and dilute if it's full and saturated with only a small amount of solute in it. So the graphs we're about to be looking at are going to show us the different amounts of solute that represent saturated for different substances. So that's what we're getting into real soon. Then these 2 other words, miscible is almost the same thing as soluble. It's just referring to 2 liquids instead of a solid and a liquid like we usually talk about with soluble. So 2 different liquids can be miscible if they are soluble in each other. And because soluble still works for liquids and solids, we generally just use that. Immiscible, just like insoluble, is when 2 liquids are not soluble in each other. So just a couple extra little vocab words to use as we're looking at things. And then at the top of page 6, we've already talked about how temperature can affect some solubility things. The solubility of most solids, as we talked about in class, does increase as we heat things up. Speeding up those molecules helps break down those solids into our liquid in order to make it soluble. But the reverse is actually true with gases. As we get particles moving faster, our gases have a harder time staying in our liquid. Remember that in general, our solids move the slowest, liquids move a little bit faster, and gases are the fastest. So if we're trying to get our gases to be stuck in this liquid, in a liquid aqueous solution, we actually need them to slow down a little bit more in order to be able to fit and kind of hang with those liquid particles. So reducing the temperature generally helps our gases be more soluble, which is why sodas, if you leave sodas out on the counter or outside on a hot day, they tend to go flat faster. And we keep most of our sodas in the fridge, especially after they've been opened, because that will help keep that dissolved gas, that dissolved carbon dioxide, dissolved into our soda liquid the best and for the longest. And the same kind of thing is true with fish. Fishermen are going to find the largest fish in the deepest part of the lake on hot summer days. And that's because that deeper, colder water has more dissolved oxygen. Of course, the fish want the most oxygen as possible for the least amount of effort. But it's that more oxygen part that is the key here. Okay, so just to get you a quick introduction to these graphs and charts, I want to point out a few things about them first, and then we're going to go over the first 3 questions, which is not these. These are just things I want you to notice. Anytime we get a new graph or chart, you should definitely look at your X and Y axis. Over here on the Y axis, that tells us how many grams of our solute dissolved. And on the X axis, we have temperature measured in Celsius. So those are our axes. If we're given those kinds of numbers, we can follow those and find a point on the graph. Now, our different substances. We got a lot of lines on the chart. Each of those lines represents the solubility, the saturation level, where that specific solution or solute is saturated in a particular kind of solution. So that line is saturated, and we can compare all different saturation points and solubilities of different substances using the same graph. And thirdly, these graphs are made around having a specific amount of water, because if we had more water, more would dissolve. So we have to set a standard, and our standard is 100 grams of water. That is actually also equal to 100 milliliters of water. So as long as we have 100 of that water stuff, no matter whether it's grams or milliliters, then we can read the numbers and answer our questions directly off of this graph. It's only if it's not 100 milliliters or 100 grams of water that we might have to do some special stuff. And the questions are going to be pretty simple. It's all just reading a graph. So after you pay attention to those axes and you read these questions carefully, you can basically already answer most of this probably. So we want to know the solubility of a saturated solution. So saturated is where our lines are, of KNO3 at 10 degrees Celsius. Well, I'm going to go find my KNO3 line and then find 10 degrees Celsius. And if I follow that up to my KNO3 line, it is going to hit just above 20 grams. And that is the solubility of KNO3 at 10 degrees Celsius. That tells me how much will dissolve, about 21 grams. Now, if you thought, I think that's closer to 22 or 21 and a half, that's fine. We are not going to be paying attention to sig figs. We're not going to use these in calculations. This is just helping answer some simple questions. So, just reading numbers off the graph, following the x-axis up to the line, and then over to the y-axis. This second question asks us which compound is going to be saturated if 80 grams are dissolved in 100 grams of water at 50 degrees Celsius. Now this one has a whole lot more numbers in it, but keep in mind that 100 grams of water is just telling us that we can read these numbers and use this specific chart. So we don't really care about that right now. That's not actually going to help us. If I'm going to look at numbers on my chart, I'm going to try and see where that 80 grams and our 50 degrees Celsius are going to intersect, and they happen to hit each other and intersect right here, which also happens to be where our KNO3 line. So that must be the compound that is saturated at that point, because our lines represent where our compounds are saturated. So that's the line I see there. So it really is that simple. Now, of course, they can and will get a little more complicated. Like this next one starts to ask you about that saturated, unsaturated, or supersaturated thing. What if I don't want to change the solution by adding any more crystal? How can I answer that question? Well, using this chart, of course. So this tells us that we're dealing with sodium nitrate, which is going to be NaNO3, this line right over here. And that's 100 milliliters of water, good. So now I'm going to be looking at where 140 grams and 65 degrees Celsius intersect. So at 65, our intersection point is about here. And that point is over the line. And what we call solutions that are oversaturated is supersaturated. If my point had been under my line, if I had to go from my line down to get to the point that it was talking about, my solution would be unsaturated. And only if it was exactly perfectly on that line would it be a saturated solution. So this solution is super saturated because those two values point to a point that is above my sodium nitrate saturated line. So that's our intro to these problems. You can probably give a couple more of these example problems a try, but we'll go over them in class and then do all of that next worksheet and then learn something else. So hopefully this isn't too tricky.